are going to find the magnetic field due to infinitely long straight wire carrying current. Applying the BIO SAVART Law. Let us consider a current carrying conductor or long current carrying conductor carrying current I. Let us consider a long straight wire XY carrying current I. We take a point P which is at a distance R, rather A, at a distance A, that is OP, which is perpendicular distance of P from the wire XY, is the distance A. OP is equal to A, which is the distance of the field point from the straight current, right? We are going to find the magnetic field at point P. Now to calculate the field, we have to take a very small current element ideal. We take a very small current element ideal at a distance L from O. At a distance L from O, we take a very small current element ideal, which is at a distance R from the point P. That means this is the current element whose direction of current element is upward, and this is the direction of the displacement vector, that is R. The angle between ideal and R is alpha, and let us say this angle is theta. Now, according to BIO SAVART Law, magnetic field at point P due to this current element is dB equals to ideal mu naught by 4 pi ideal cross R divided by R cube. Now, first we find the direction. What will be the direction? This is ideal and this is R. Now rotate a right-handed screw from ideal to R. From ideal to R. That means rotation is clockwise. Then screw will advances into the bolt. That means field at P due to this current element is perpendicularly into the bolt. This is dB, right? This will be the direction of dB. Now magnitude of dB is dB equals to mu naught by 4 pi ideal R sin alpha divided by R cube, because alpha is the angle between ideal and R. That's why ideal R sin alpha by R cube. This is the magnitude, which is equals to mu naught by 4 pi ideal sin alpha by R square. Now I have to find the magnetic field due to the entire current or entire conductor, current carrying conductor. Now see here, let us write this point as M. Then from triangle OMP we get, from OMP, this angle is 180 degree minus alpha. This is theta, this is 90 degree. Therefore we can write 180 degree minus alpha plus theta plus 90 degree equals to 180 degree. Therefore minus alpha plus theta plus 90 degree is equal to 0, or we can write alpha is equal to theta plus 90 degree. Therefore dB equals to mu naught by 4 pi IDL sin theta plus 90 degree divided by r square. And again, from here you can write L by A is equal to tan theta. Therefore, L equals to A tan theta. And from here you can write dl d theta is equal to A sec square theta. Therefore, you can write dl equals to A sec square theta d theta. Right? We again r square is equal to L square plus A square. R square is equal to L square plus A square. And L is equal to A tan theta. Therefore, you can write A square tan square theta plus A square. A square into tan square theta plus 1. And tan square theta plus 1 is sec square theta. Therefore, r square is equal to A square sec square theta. Now, putting these things in this expression, we can write dB equals to mu naught by 4 pi I dl can be replaced by A sec square theta d theta. A sec square theta d theta. Sin theta plus 90 degree is cos theta. Divided by r square can be replaced by A square sec square theta. A square sec square theta. Therefore, we get that mu naught I cos theta d theta divided by 4 pi. 1 cancels out, sec square theta cancels out. That's why you get mu naught I d theta into cos theta. Right? In the denominator 4 pi into A. 1 cancels out. This is dB. That is the field due to this current element. Now, the magnetic field due to the entire conductor. That means if first we take the conductor as finite, that means it is from x point to y point. Let us say at the lower end point theta is equal to minus theta 1 and higher end point the angle is plus theta. Why this is minus theta 1? Because we have take this angle is theta. Now if we take into account this point, then I have to go in this direction. That's why this angle is minus theta 1, but this angle is in the same direction of theta. That's why this is taken as plus theta. Now, to get the magnetic field at point Q due to this xy conductor, current carrying conductor, I have to integrate this term or this dB starting from x and it will end at y. That means total magnetic field or the resultant magnetic field at point B due to xy is equal to integration dV, and integration will be carried over from x to y, and that will be theta equals to minus theta 1 to plus theta 2 mu naught I cos theta, mu naught I cos theta d theta divided by 4 pi a. Now mu naught I by 4 pi a, which are constants, that's why it can be taken out of the integration and you get integration cos theta d theta. We know cos theta d theta, integration of cos theta d theta is sin theta, and limit is theta is equal to minus theta 1 to plus theta. Therefore, we get mu naught I by 4 pi sin theta 2 minus sin of minus theta 1, our limit minus lower limit, and we get mu naught by 4 pi mu naught I by 4 pi sin theta 1 plus sin theta 2. This is the magnetic field at point P due to the whole current carrying conductor, that is XY conductor. Yes, there will be a mu naught I by 4 pi a. Here also mu naught I by 4 pi a sin theta 2 minus sin minus theta 1, and sin minus theta 1 is minus sin theta 1, that is minus minus plus, and that's why you get mu naught I by 4 pi a sin theta 1 plus sin theta 2. Now we are going to find some special cases, that is if the straight wire is infinite in length, then if this is infinite, then it will go in the downward direction. That means theta 1 increases, and at infinite it will make 90 degree. Similarly, in this direction the length is infinite and theta 2 is increasing, at infinite it will 90 degree. That means for infinitely long conductor, infinitely long straight current carrying conductor, theta 1 equals to 90 degree, and also theta 2 is also 90 degree, and in that case the magnetic field at point P is equal to mu naught I by 4 pi sin 90 degree plus sin 90 degree. That means you get 4 pi a 1 plus 1, that is you get mu naught I by 4 pi a into 2, or you may write mu naught by 4 pi 2 I by a, and also you can write this as mu naught I by 2 pi a. This is the magnetic field due to an infinitely long straight current carrying conductor at a distance a. Now, if the conductor is semi-infinite, semi-infinite means let us say conductor starting at here and it extends up to infinity in the lower direction, or starting here the conductor in the upper direction it extends up to infinity. That means field point is here, conductor starts here, right? If in the upper direction it goes up to infinity, then theta 1 is equal to 0 degree, because it starts from here, theta 2 is equal to 90 degree. And if it extends in the lower direction, starting here, then theta 2 is equal to 0 degree, theta 1 is equal to 90 degree. Then for that case, the magnetic field is equal to mu naught I divided by 4 pi a. We have to write sin 90 degree plus sin 0 degree. If it is in the upper direction, then theta 2 will be 90 degree, theta 1 0 degree. If it is in the lower direction, then theta 1 will be 90 degree, theta 2 will be 0. From here you can write mu naught I by 4 pi a, because sin 90 is 1, sin 0 is equal to 0. 1 plus 0 is equal to 1. And again, third case also I want to discuss, that is if the field point is along the wire. If the field point is along the wire, that means if the field point is here or field point is here, then if field point is along the wire, then what happens? Now see here, you have to think about this. Just concentrate here. If the point is here, say here, then what happens? Then This is our A, right? And this, like this, right? That means this angle, right? This angle will be theta 1 and this angle will be theta 2. See here, this angle is theta 1, this angle is theta 2. And if the point comes closest to the line of the conductor, then this theta 1, theta 2 both are increasing and both tends to 90 degree. But see here, theta 1 is positive, it is negative. Here negative term already here. That means theta 1, which is in the lower direction, that means I have to minus 90 degree. But see here, theta 2, which is in the upper direction in our calculation, but here it is also lower direction. That means you have to put theta 2 is equal to minus 90 degree. Right? We have to put theta 1 is equal to 90 degree. Already we have a negative sign here. That's why you have need not to put any negative sign to the 90 degree. But since this is plus sign, so I have to put theta 2 is also minus 90 degree. That's why the magnetic field at this point, I have taken first here and now going close here. Then this angle is also 90 degree, this angle also 90 degree. But theta 1, which is already negative, that means it is 90 degree, but theta 2 is minus 90 degree. Then I have to put here mu naught I by 4 pi sine 90 degree plus sine minus 90 degree. That means mu naught I by 4 pi, this is 1, and sine minus 90 degree is equal to minus sine 90 degree. That means minus 1. 1 minus 1 is equal to 0. That is the magnetic field due to a straight current at a point on the line joining the conductor will be 0.